Hello calculus students, here we are with integration by substitution. Our last section here, we're not going to be covering 6.6. We're going to use pattern recognition, and basically it's sort of like the chain rule in reverse. Remember how the chain rule opened up a lot of different derivatives we could do? Now this is going to open up a lot of different integrals we can do. And toward the end there we're going to see how to evaluate a definite integral involving an even or an odd function. Now pattern recognition, this is also called U substitution. When you see that there is basically a derivative of the inside of the function hanging out somewhere else inside the integrand. Now remember the chain rule? Derivative of f gx is f prime of gx g prime of x. So if you have this pattern inside an integral, you can take it back then. And here's the theorem. Antidifferentiations of a composition of functions, f of g of x, g prime of x, has to be in the integrand. If I don't have this g prime of x in here, I'm not going to be able to do it. And so you take the antiderivative f of gx plus some constant integration. You can also do what we call u substitution, let u equal g of x. So you get f of u du equals big F of u plus c. So you're going to have an outside function, inside function when you have this composition of functions. And you got to make sure the derivative of the inside function is also in the integrand. So let's see how this works. Recognizing this pattern, find the integral. So what we've got here is we can think of u as x squared plus 1. That's your inner function. You've got a composition of two functions. You've got squaring and you've got x squared plus 1. And the squaring is the outer function. So du is 2x dx. So all of this becomes our du, and this is u squared. That's the. So yeah, it's just my sister. Let's take a look here. Here we are. We let u equal x squared plus 1. It's the inner function. So now we've got the integral of u squared du. And that's a lot easier to integrate because we can just say u to the third over 3 plus some constant integration. Just don't forget at the end that you got to change the u back into x's. X squared plus 1 quantity cubed over 3 plus c. Okay? Now you could have possibly expanded this out and then distribute the antiderivative over the additions. But this is so much easier. Here, in this one, we're going to let u equal 5x plus 1. That's the function inside the square root. So du becomes 5 dx. So this becomes the integral of 5 square root of u dx. I can rewrite it as square root of u times 5 dx, so I can replace all of 5 dx with du, square root of u du. So this is 1 to the u to the 1/2. So we can take the antiderivative of this u to the 3/2 over 3/2 plus c. And then you can wrap up by, put that in the wrong spot, by calling it 2u to the 3/2 over 3 plus c, and then unsubstitute the u. Replace the u with 5x plus 1. 3/2 over 3 plus c. Now you can always check these by taking their derivatives. And also you can check them with your TI-89. And here's the trick for the TI-89. On this last one, with your integral of 5 square root of 5x plus 1 dx. So you can say integral. Alright, notice when you do this on the 89 and go, this squiggle, this integral symbol is above the 7. And you go left parentheses 5 times square root, left parentheses 5x plus 1, right parentheses, comma, x. It actually gives you the answer to 5x plus 1 to the 3/2 over 3. Do you see the difference? It's missing something very key. Missing the plus c plus the constant of integration. So make sure if you're doing these on your calculator, you're aware that the calculator is not going to give you the whole solution set. Now let's explore some patterns here. The integrand in each of the following integrals fits the pattern f of g of x, g prime x. Identify the pattern used the result to evaluate the integral. And it's very similar to, so in this case, let's just identify our u's and our du's. Here on this one, u is x squared plus 1. That's the inner function. And du is 2x dx then. And you have that available. Here, u equals x cubed plus 1. That's the inner function. And so du is 3x squared dx, and that's available. But notice a slight difference here in C and D. In C, the 2 isn't there. So what we find ourselves doing is sneaking a 2 in here and compensating by putting a 1/2 outside the integral symbol. And then we can proceed as normal. Same thing here. We need a 3x squared, so we put a 3 inside the derivative and multiply by 1/3 outside. This is totally legal because constants can move in and out as factors from the integral symbol. And this is the key idea here. See how that constant k, that's in the integrand right now, on the right side, I've moved it outside the integral symbol. So that's what we're going to need here in this first one. Find x squared plus 1 quantity squared dx and find this integral. Well, we let u equal x squared plus 1 because clearly that's the inner function, the function inside the squaring. So du is 2x dx. Well, we've got the x and the dx, but we don't have a 2. So we are going to sneak a 2 in there. Going to sneak a 2 in there like that. I can't just multiply the whole thing by 2. I have to compensate by multiplying the whole thing by half as well. A half times 2 is 1. But I've decided to move the 2 inside the integral and leave the 1/2 outside. So now we have 1/2 integral of x squared plus 1 squared 2x dx. And now all of this is our du. And this is u squared. So we've transformed it into 1/2 the integral of u squared du. And that's an easy enough antiderivative here. U cubed over 3 plus some constant integration. And it doesn't matter if you include the constant multiplied by the half because a half times a constant is still going to be a constant. So we get u cubed over 6 plus a constant. And now unsubstitute the u to say x squared plus 1 quantity cubed over 6 plus a constant for your antiderivative. Now, be careful though. What you cannot do, if it's in this problem we had an x squared plus 1 quantity squared dx, you couldn't just pop a 2x in here and a 1/2x in there because now you're moving a variable inside and out of the antiderivative symbol, and that's not correct. There is a way to take on this one, and you'd have to do it by expanding out and going x to the 4th plus 2x squared plus 1 dx, and then cranking everything up. X to the 5th over 5 plus 2x cubed over 3 plus x plus some constant integration. But that is not what we call the substitution technique. That's sort of a brute force technique, and that's not how it's going to be available to you. So sometimes you're going to find you just can't do the integral. Now, change of variables is what we've been doing along here with this whole idea of u substitution. That here our variable is x because it says dx right here. Here the variable is u, du. This affects us when we start doing the limits of integration. Now, another thing too is this one doesn't seem so obvious here. But if we let u equal the square root of 2x minus 1, we might be able to get somewhere. Let's let u equal 2x minus 1, the thing inside the square root. So du is 2 dx. So all we need to sneak into here is a 2 in front of that dx. So I compensate with a 1/2 out here. So it becomes 1/2 antiderivative of square root of u du. And the square root of u is u to the 1/2 power. So now we can take the antiderivative. 1/2 u to the 3/2 divided by 3/2 plus your constant integration. Now that's going to be 1/2 times 2/3 times u to the 3/2 plus c, or 1/3 u to the 3/2 plus c. Still not done though, because we have to replace the u with 2x minus 1. So it's 2x minus 1 to the 3/2 over 3 plus c. And you can always check it by taking the derivative of the thing to see if it works out. Kind of like when you did factoring in the past. you could check it by doing the derivative. You could check it by actually multiplying out. So the same thing here. If you do an integral, which is the reverse of differentiation, you can check your integration by doing a derivative. So let's do the derivative of this. It would be the derivative of our answer would be 1/3, that's a constant multiplier. The 3/2 comes down in front. 2x minus 1 would be raised to the 1/2, 1 less power. And you have to multiply by the derivative of the inner function, so that's 2. The 3's cancel, the 2's cancel, and you get the square root of 2x minus 1. And sure enough, that was our integrand. Check. Here we go with change of variables again. Now we're going to let u equal 2x minus 1. See how this problem is slightly different? So du is still 2 dx. But now we've got some issues here because we've got an x sitting over here. But there's another substitution we can do here. Because if I do this now, I'm going to have square root of u, and even if I put the 2 in there, I'll get du. But I still have this x here. Well, let's at least sneak the 2 in and the 1/2 out here. So we have 1/2 integral of x square root of 2x minus 1, 2 dx. And so this part we can change into the square root of u. This part can change into du. But what about this leftover x? Well, you could take a look at your original substitution and say, hey, well, I can solve that for x. I can say u plus 1 equals 2x. So x equals u plus 1 over 2. And that's what we can put in here, u plus 1 over 2, and then there's this half. So let's pull this half out again. So we have 1/4 antiderivative of u plus 1 times the square root of u du. Now remember, you can't distribute the derivative, antiderivative over multiplication. And there's no product rule for you either. So what we're left with then is distributing this and writing it as u square root of u plus square root of u du. And so this is 1/4 antiderivative of u to the, this is u to the first, u to the half, so this is u to the 3/2, and this is u to the half du. And now we can take the antiderivative. U to the 5/2 over 5/2, I'm just going to write that as 5 over 2 like that, plus u to the 3/2 over 3/2, so we put the 3 down here and the 2 up here, plus our constant of integration. So we have 5u to the 5/2 over 8 plus 2u to the 3/2 over 3 plus c. And then it's just a matter of unsubstituting. Remember, u is equal to 2x minus 1. So you got 5 times 2x minus 1 to the 5/2 over 8 plus 2 times 2x minus 1 to the 3/2 over 3 plus your constant integration. And we can go ahead and check this with the TI-89 check. Let's do the TI-89 check on this one. Just because there was a lot going on. Integral of x squared of 2x minus 1. Integral of x squared of 2x minus 1 dx. So you do the integral symbol, left parentheses x times square root, left parentheses 2x minus 1, right parentheses, comma, x. Just like that. And let's see what we get. Okay, so the TI-89 says 2x minus 1 to the 3/2 times 3x plus 1 over 15 when I do this. Now this says to me that maybe it's more than just a slightly different form. I can see how they factor out the 2x minus 1, but I was wondering what happened to my 8. So I go back and I go, hello, right here. When I did this integral of u to the 5/2, it should have been 5 here and 2 up here. So a little too hasty there. Let's fix that. This should be a 5 here and the 2 up here. So that's going to change this fraction to a 1/10. So this fraction is wrong. 2/20 or 1 over 10. And then when we substitute in, it's over 10. 2x minus 1 5s plus over 10. Still, do we have the answer we have over here? They had 15. Well, let's check my answer. If I use an LCD of 30, that means I'm going to have 3 times 2x minus 1 to the 5 halves, plus, multiply this by 10, 20 times 2x minus 1 to the 3 halves, all over 30, plus my constant. And then looks like they factored out 2x minus 1. So let's try that. 2x minus 1 to the 3 halves. That's going to leave behind 3 times 2x minus 1 to the first, plus 20, all over 30. So I'm getting 6x minus 3 plus 20 all over 30. I'm still seeing some kind of mistake here, because I'm getting 6x minus 17. That's not reducing like here, so I'd expect that something else happened in here. When you factor the 2x minus 1 to the 3 halves out of that, it should have just left the 20. Now, so let's find out what else we might have erred on here. U to the 3 halves, U to the half, that's correct. U to the 5 halves, and then divide by 5, that's a 5 and 2. U to the 3 halves, and then divide by 3 halves, so that's 3, and the 2 goes up there. That all seems fine. Oh, I know. It's the 1/4 did not get distributed here. Oh, hello. So here we go. This should be 1 over 6. Let's make that a 6, because I forgot to multiply the 1/4 into both these terms. Yep. So when we get over here, this is over 6. So we can still use an LCD of 30. So our LCD is still 30, putting these two ideas together. And when we do that, that thing might be, did we do du right? Yeah, 2 dx, yeah, that's fine. We still have that 2 in there, and that 1/2 outside, right, that's fine. So if I do an LCD of 30, we have to multiply this fraction by 3 over 3, we did that, and this fraction by 5 over 5. So let's make that a 5. So now we have 2x minus 1 to the 3 halves times 3 times 2x minus 1 plus 5. And this is looking much better. So 6x minus 3 plus 5 is 6x plus 2, 2x minus 1 to 3 halves times 6x plus 2 over 30. We'll look at that. We can factor out a 2 from this to get 3x plus 1, and a 2 from the bottom, and sure enough, now they agree. 2x minus 1 to 3 halves times 3x plus 1 over 15. Let's try change of variables again. Looks like a very similar problem, but now we have the advantage of when we have u equal to x squared minus 1, du is 2x dx. And now this x comes in handy for us, because we can write this as the integral of square root of x squared minus 1, x dx, and sneak in a 2 here to finish up our du, and put a 1/2 out here. So it becomes 1/2 the square root integral of the square root of u du. So that's 1/2 integral of u to the 1/2 du. And so that's 1/2 u to the 3 halves over 3 halves plus the constant. 1/2 times 2/3 u to the 3 halves plus the constant. So 1/3 u to the 3 halves plus the constant. And now let's put in our original u, which is x squared minus 1. Oh, God. X squared minus 1 plus the constant to the 3 halves. Okay. And let's check that quickly on the T99 as well. And it checks out on the T89. Now here's some guidelines for making the change of variables. Choose a substitution u equals g of x. Usually it's best to choose the inner part of a composite function such as a quantity raised to a power. Then compute du equal to g prime of x dx. Rewrite the integral in terms of the variable u. Find the resulting integral in terms of u. Replace u by g of x to obtain an antiderivative in terms of x. And check your answer by differentiating. And here's the general power rule for integration. This is a typical example of a substitution where you've got some inner function raised to the n. So take the antiderivative, you want to go g of x to the n plus 1 divided by n plus 1 plus c. But you've got to make sure that g prime of x is there inside the integral as well. So here's a few examples of substitution general power rule. Let's just try and identify in each of these quickly what you would use for u. So what's your u here? What do you think? What's the inner function? That's right, 3x minus 1. And so du ends up being 3 dx. And that's the idea. There's your 3 dx, and it's available too. Now, you don't have to actually, if you set this up like this, you don't have to show me the u substitution, but it's usually pretty handy. It's going to be handy when we do definite integrals as well. Okay, what's our u in this case? Well, we've got a couple functions. Now, you could just expand it out. But why, when you can recognize this one? Now, neither of these is really inside, but which one's the derivative of the other? Is x squared plus x the derivative of 2x plus 1? No. Is 2x plus 1 the derivative of x squared plus x? Yes. So we let u equal x squared plus x. So du is 2x plus 1 dx. And that's what we have here then. So you can write all this as your du. Here in this one, what's the inner function? The thing inside the square root. So we'll make that x cubed plus 2, or x cubed minus 2. And du becomes 3x squared dx. So you can see we're going to have to do a little prepping here. We don't quite have the full dx. We got x squared dx. We need a 3 in here. And so we put a 1/3 outside there. And that's that roll, that 1/3 and 3 in there. Here, now things are sneaking into the bottom. And that's okay. We can still look at that as the inner function, 1 minus 2x squared. So du becomes negative 4x dx. And so we can see we got the x and the dx. We just need a negative 4 up here, so we're going to put a negative 1/4 outside. And that seems to work, doesn't it? Okay. Now they end up like not actually calling it u, but they kind of show it here in red above it, u to the negative 2 du. That cranks up a power u to the negative 1 over negative 1. That's how you get that part. Okay, suppose you're asked to find one of the following integrals. Which one do you choose? And explain your reasoning. Would you like this one or this one? Well, in either case, you would probably pick u to equal your inner function x cubed plus 1. And then du would be 3x squared dx, which we could find here. So that's why we choose this one and say, ooh, let's not do that one. Let's actually ask the calculator what that works out to be. Well, the calculator tried this one. This square root of x squared, x cubed plus 1. And it gave it this bizarre answer that comes from something called integration by parts. So it's nice to know that the calculator gets stumped sometimes too. And sometimes there are some integrals that just can't be done. It seems like we can do anything with derivative rules and the chain rule idea, but not so much with antiderivatives. Now, some integrals and integrants involve quantities raised to powers cannot be found by general power rule. Consider these two integrals here, x times x squared plus 1 squared and x squared plus 1 squared. If you do the u substitution on the left one, but you can't do it over here because you don't have the du. U equals x squared plus 1. So du is 2x dx. So we're ready to go on this one. This one, though, you'd have to, like I said before, expand it out and then take the integral of each part. Now, for definite integrals, you've got to make sure that you're changing the limits of integration as well. So on this one, we get u equals x squared plus 1. That's our inner function. And du then is 2x dx. So we can manage to actually get our du in there with a 2 here and 1/2 out here. But what you also have to consider is the limits of integration. The limits of integration right here. Those are actually saying that x equals 0 and x equals 1. So when we do our u substitution, you have to consider that and say, oh, put 0 into this formula, and you get u equals 0 squared plus 1, or 1. And put 1 to this formula, so we get 1 equals 1 squared plus 1, or 2. So even though x goes from 0 to 1, now when we set up the u integral, we're going to go from 1 to 2. And then x squared plus 1 is u cubed du. And then we do this antiderivative, u to the 4th over 4, but we evaluate it from 1 to 2. So we get 1/2, 2 to the 4th over 4, minus 1 to the 4th over 4. And so that's 1/2, 16/4 minus 1/4 is 1/2 of 15/4, which is 15/8. There we go, check. So now some people will sit there and they'll do the antiderivative and then they'll put the x squareds back in. And that's fine if you want to do it that way. I just think it's more efficient this way. It makes this antiderivative less complicated as long as you remember to change your limits of integration as well. Okay? Now here's a person, they did this without ever doing a use in there. Okay? If you use pattern recognition, not do the u substitution. And that's fine. Nothing wrong with it doing it that way. Let's try our change of variables again on this one. We let u equal 2x minus 1 because that's an inner function. So du is 2 dx. So we can take care of that right away. There's our 2 dx and our 1/2. But notice also you still have an x left over there. So we're going to have to solve this for x and say u plus 1 equals 2x. So x equals u plus 1 over 2. And I think we're just about ready to substitute everything in, except we should look at x and u. Remember, u equals 2x minus 1. So if x goes from 1 to 5, u is going to go from 2 times 1 minus 1, which is 1, to 2 times 5 minus 1, which is 9. So u is going to go from 1 to 9. Let's incorporate that all into our integral now. We have a new integral, 1/2. And instead of from 1 to 5, we're going to say u goes from 1 to 9. And we've got a 2 in there, but that 2 is part of making the 2 dx. That's du. And x is u plus 1 over 2. So this is u plus 1 over 2. That's just for the x. 2 dx becomes our du over the square root of u. So we can stick that 1/2 outside. 1/4 antiderivative from 1 to 9. Of u plus 1 over the square root of u du. And you can continue to write these then. U over the square root of u plus 1 over the square root of u du. So 1/4, and we're going from 1 to 9. The integral of u to the 1 over u to the square root of u to the half is u to the half. So this is u to the half plus u to the negative 1/2. Du. Now we're finally ready to crank it up. U to the 3/2 over 3/2, I'm going to put the 2 up here, plus u to the 1/2 over 1/2, which would put the 2 up here, evaluated from 1 to 9. We can distribute through with the 1/4 there. So we get u to the 3/2 over, 6, plus u to the 1/2 over 2, evaluate from 1 to 9. Now let's put the 9 in. 9 to the 3/2 over 6, plus 9 to the 1/2 over 2, minus, now we're going to put the 1 in, 1 to the 3/2 over 6, plus 1 to the 1/2 over 2. And so now this you can just kind of all punch out in your calculator there. 9 to the 3/2, well, you can take the half root first, that's 37. I'm sorry. 9 squared is 3, cubed is 27. 27/6 plus 3/2 minus 1/6 plus 1/2. And some tricks you can do on here is maybe deal with the two fractions the same there, so we get 26/6 plus 3/2 minus 1/2 is 2/2 plus 1. So that's 13, take out a 2, 13/3 plus 1. 13/3 plus 3/3 is 16/3. And I believe that checks. So there you go. Our last little tricks here are integration of even and odd functions. And if you integrate an even function from -a to a, like down here, notice how because of the even symmetry, you're going to have the same thing on the right half of the y-axis as you do on the left. So it's just like taking the area from 0 to a and doubling it. So that's a little trick you can do with even functions. With odd functions, notice how this left half and the right half are going to be exactly opposite each other in terms of area, because this is positive area when it's above the axis, negative area when it's below. And so when you go from -a to a for f of x dx, you always get 0 on an odd function. So let's integrate this odd function here. We can crank it up and say x to the 6th over 6 minus 4x to the 4th over 4 plus 6x squared over 2 evaluated from -2 to 2. So that's x to the 6th over 6 minus x to the 4th plus 3x squared evaluated from -2 to 2. Now we're going to evaluate from -2 to 2. So we're going to do the 2 first and subtract off this. So we have 2 to the 6th over 6 minus 2 to the 4th plus 3 times 2 squared minus -2 to the 6th over 6 minus -2 to the 4th plus 3 times -2 squared. So that's 64th sixths minus 16 plus 12 minus 64th sixths minus 16 plus 12. Well, that's the same thing. This is 0. We should have known that right along, right? Because we took the integral of an odd function from -a to a, from -2 to 2, and that'll always be 0. The stuff up here is canceling out with the stuff over here. Silly Mr. Lang. But you know why I did that. I wanted to kind of give you sort of a mini proof of why this happens. Because when you take these odd powers and you crank them up, they're all going to become even powers. And when you're on the same, when you put the, see how we put the -2 in? That negative got raised to even powers, so you were subtracting the same thing from the same thing. That's why all ended up being 0. Little mini proof. Okay, flange out.